Okay, 7th grade. So we're going to pick up where we left off, which is with Section 7, Chapter 9, Independent, Dependent Events. Independent events are two things where whatever happens the first time doesn't affect what's going to happen the second time. Think flipping a coin, taking a marble out of a bag and replacing it. Okay. These are examples of no matter what you do the first time, the second time, we've reset the situation, probabilities remain the same. Dependent events, on the other hand, are where whatever happens in the first event affects the chances of the second event happening. So, for example, if there were 10 marbles in a bag and we drew one out, the probabilities have now all changed for the next marble because there's only 9 marbles remaining. So our first probability would be a number over 10, whereas our second probability would be a number over 9. Okay. So the first thing that we have here for examples are determining if a situation describes independent or dependent events. So let me grab a pen here so I can write, and bear with me, my writing is gonna take me a little while to get used to writing on this thing. Okay, so coin landing heads on one toss and tails on the next. This describes independent events, which I am going to abbreviate IND, because a coin landing either on heads or tails would have no effect on how it's going to land the next time. It's an entirely new experiment, a new trial, I should say. And it having landed on heads doesn't change the fact that the next time it's still got a 1/2 and 1/2 chance of landing heads or tails, respectively. Our next example, drawing a heart and a spade from a deck of cards without putting the first card back. Okay. So there are 52 cards in a deck. The probability of drawing any given suit from a full deck is 13 over 52. There are 13 cards of each suit. So the probability of drawing a heart on the first draw is 13 over 52. Now the assumption is we're not putting that back. It says right there, without replacing the first card. So that means to draw a spade now, there are 13 spades, but there are only 51 cards total. That is not the same as 13 over 52. Drawing the heart affected, it changed the probability of drawing the spade. So this describes dependent events. So DEP, dependent. And here we've got ourselves a couple of formulas. If events are independent, then the probability of A and B both happening is the probability of A happening times the probability of B happening. Whereas if they are dependent, the probability of A and B happening is the probability of A times the probability of B after we account for A. Okay. So let's do some examples of both independent and dependent events. So our first situation here, we have a fair spinner, which means everything's equally likely, and it's got 5 numbered sections, 1, 2, 3, 4, and 5. We're being asked to find the following. Okay. This describes independent events, because no matter what you spin, each time, each section still has a 20% chance of landing on each number. Okay? It's a fair spinner. Every time you do it, the probabilities remain the same. So the probability of spinning 3 5s. Well, the probability of spinning 1 5 is 1/5. Makes sense? 1 5, 5 numbers. Formulas say to multiply. The probability of spinning a 5 the second time is still 1/5, and the probability of spinning a 5 the third time is 1/5. So we just have to multiply straight across. None of these fractions simplify, so our answer doesn't simplify. 1 times 1 times 1 is 1. 5 times 5 times 5 is 125. If I were you, I would leave the answer as a fraction, because this isn't going to be a very pleasant decimal. So I'm going to erase that so I've got room to work here. Now the probability of spinning 3 odds is a little different, because we have to look at this and say, what's the probability of spinning any odd? There are 3 odd numbers on the spinner, 1, 3, and 5. So there are 3 outcomes I like, and there are 5 outcomes total. So here, since my probabilities don't change, these are always independent, going to have 3/5 times 3/5 times 3/5, which is 27 125ths. Again, since none of my fractions simplify, I don't need to worry about simplifying an answer. We're good. Now comes the strange boy. Okay. We're going to talk about the probability of spinning at least one 5. And I do not want to do a whole lot of work here if I don't have to. So you need to cast your mind back to early in the chapter. We talked about two events being complements of each other. Okay, way back it was probability of rain and the probability of not rain. They add up to be 1. Same thing with the probability of snow and the probability of not snow. If you can identify two events that are complements, then we can use this property to help us. So what is the opposite of spinning at least one 5? It's spinning no 5s. Okay, so the probability of spinning at least one 5 is equal to 1 minus the probability of no 5s. That first thing is supposed to be a parenthesis. Like I said, you'll have to bear with me. Writing here is going to take some getting used to. So the probability of no 5s. How many answers do we like here now? On each spin, there are 4 answers we like. There are 4 numbers that aren't 5. So we're going to have our 1, and we're going to take away 4/5 on the first spin times 4/5 on the second spin times 4/5 on the last spin. Okay. Well, again, none of these fractions simplify, so we can multiply straight across. 4 times 4 times 4 is 64, and 5 times 5 times 5 is 125, as discussed earlier. So I'm going to do that over here because I've got the room. 64 125ths, and we're still doing the 1 minus that because remember, order of operations, we have to do all the multiplying first. So let's make our lives a little simpler. Let's turn that 1 into 125 over 125. We're going to subtract 64 over 125. And let's see, 125, take away 64, should be, if I've done my mental math correctly, 61 over 125. And again, I'd probably leave this as a fraction. So those are independent events, where all we have to do is find the probability of each individual event and multiply them all together. The opposite are independent events. So here we've got a drawer that has 10 black and 6 blue socks. And for whatever reason, this strange individual doesn't pair their socks. So we're going to find the probability of drawing out a pair of black socks, and then the probability of drawing a pair of the same color of socks. Okay. So what we're looking at here, the first time, in order to draw a pair of black socks, I'm finding the probability of drawing black, then black. So there are 16 socks total. The first time, the probability of black is 10 over 16, as we would expect. But the probability of drawing another black sock is not 10 over 16. It changes now, because there are only 9 black socks and 15 socks total. So we have 10 sixteenths times 9 fifteenths. Is there simplifying that we can do here? Absolutely. I see 10 and 15, so I'm going to make that 2 and 3. I see 3 and 9, so we're going to make that 3 and 1. And 2 and 16 become 1 and 8. So we will multiply straight across, and we'll have our probability. 1 times 3 is 3. 8 times 1 is 8.